So I would like first thank you to Krystia Gniatenko and Volodya Tkachuk for the invitation that I can be a part of this great event. And I would like also to congratulate on the opening of program in quantum computing and quantum programming, and the promotion of the students specializing in these fields, especially in these hard times for Ukraine. And 1 hour ago, we had we saw how hard it can be for you. So I would like to go deeper into the science of quantum waveguides. Actually, I would like to catch the perspective, which is a relation between spectrum and geometry. And although I would like to unpack the topic from the theoretical point of view, let's keep in mind that there is a engineering behind, and such a structures like quantum waveguides can be designed. And what I mean by quantum waveguides or wires, it's a situation or it's a structure which is somehow restricted. The motion of particles is restricted in one direction, but it is free in the other direction. And usually we use in our laboratories high functioning materials like aluminum, gallium arsenide, and we can design quantum wires or quantum waveguides with various shapes. And now my question is how this shape affected the energy of the spectrum of energy, for example. And this topic is very, very wide, quantum waveguides. And I would like to start from the so-called hard-wall waveguides. These are here are examples which come from the articles which are mentioned on the slide. And what means hard-walled waveguide? It means the situation where particle can be inside the tube, for example, if we think about three-dimensional system, or strip if we have a two-dimensional system. And there are impenetrable walls on boundaries. So the particle lives inside. Suppose that there is no the other interaction, and there are only these impenetrable walls. And then the Hamiltonian of such a system, which is here very important. I mean, from the if we want to discuss energies, it has at the first look very easy form. The kinetic part, which is represented by the Laplacian, but this Laplacian acts on wave functions which are vanishing on the boundaries. And, I would like to mention from for the hard-wall waveguides. Actually, it's not the main topic of my talk, but I would like to mention here two very interesting results which states the link between geometry and spectrum. The first is that the bending of such a waveguide, which is, for example, illustrated here on the right-hand side, acts as an attractive potential which can produce bound states. So it's very important from the quantum transport, for example, because if we have bound states, we may expect that there are kind of obstacles in this quantum transport. On the other hand, the twisting, which is illustrated here and on the other picture, it acts in the other oppositely, in a sense. It acts as a repulsive potential. And for example, if we have both of these geometries in our waveguides, bending and twisting, they can just, this combination can interact, and the bound states which are induced by the bending can be reduced by the twisting. As I've already mentioned, this is a very, very wide area, and let me mention here the book of Paweł Exner and Hynek Kowarzyk, and actually the name of Paweł Exner will appear several times in my further talk, and also very interesting and general article by Dawid Krejcik. Now, the question, my question is, what is the relation between geometry and spectrum? And in the waveguide which I've mentioned, hardware waveguide, it's easier, for example, from the point of view that we can parameterize all the space where the quantum particle lives. We can parameterize by means of the curvilinear coordinates, which are consistent with geometry. For example, we can take the tangential vector and normal vector, and we can, in this way, we can parameterize the strip, or we can parameterize three-dimensional cube, for example, introducing Fresnel frame. Now, I'm going to switch to the main, to the key topic of my talk, and I would like to say very fresh results about so-called soft waveguides. And the name of soft waveguide was introduced by Exner in 2020 in one of the articles. What does it mean, and why are they soft? In this case, we admit a tunneling outside of waveguides. So we do not have any more unpenetrable walls. Now, the space which is available for the particle is the total space. It can be plane, for example, if we speak about two-dimensional case, or it can be just air-free. Now, the waveguide has a special geometry and can be modeled by a potential. So, for example, if we look at the transversal direction, we can see in the easiest case rectangular well potential. It can be just not rectangular or more general case, or it can be even partially well potential, partially it can be just a barrier. So here I will be speaking, I'm going to speak about the transversal profile. Now, let's ask the question about the spectrum, because this is what is very interesting from the point of view of the particles which lives in such a quantum system. So if we want to say something about continuum, then we have to look how the waveguide behaves asymptotically. And if we have such a waveguide which has only a local deformation and asymptotically straight, we can look at the straight waveguide first. So let's look here. We have a straight waveguide, and transversal direction, suppose that we have just this rectangular well potential, which is modeled by this potential. V is a coupling constant which says how attractive is the potential, which is located on omega. Now, what is a continuum is actually easy to see, because we in the transversal direction we have a well potential and we have discrete spectrum, a part of continuum, of course, and we have some bound states with the corresponding energies, and the ground state, so the lowest energy now in the case of completely straight waveguide, is just the threshold of the continuum. So what happens here, we have the additional part of the continuum spectrum, additional with respect to completely free situation where we have the continuum from 0 to infinity. And now we can ask the question, what about the discrete spectrum below the threshold? As I've mentioned, this question is important from the point of view of quantum transport, because bound states can lead to the obstacle, can state a kind of obstacles of quantum transport. And now these questions were posed in papers mentioned on the slide, and the answer given by Pavel Exner was quite, I mean, there was formulated a sufficient condition, quite abstract, and I would like to give you very simple examples here, which was discussed by my co-authors and myself. And suppose that we have such a simple model of quantum waveguide, which I will which can be named closing a book. Yes, so we have such a waveguide which has three parts: the straight one, and again then we have the circle one, and then again straight one. And again, speaking about the spectrum, we have to go far and to look what happens asymptotically. And asymptotically, we can see again straight waveguides, straight strips, and they are not parallel. So say the book is not closed, then the spectrum, the continuum is the same like in the case of the straight waveguide. And one can show that here, this turn of the waveguide produced discrete spectrum below the threshold of the continuum. This result was generalized by the Krejcik and Krish for that three-dimensional case, and it's interesting to mention that if we move to three-dimensional case and we take a revolution of this strip and we obtain then a layer, we can produce in this way infinite number of discrete spectrum below continuum. Now, I've mentioned that we just skip for a moment case where the strips, where the say legs are parallel, but this case was also analyzed. And but a word of warning should be said about the continuum here, because here the situation is different. Because here, if you go far and you see what asymptotically we have parallel strips, and in the transversal direction we have double walls. So the spectrum feels this, the continuum feels this, and it changes. So what it changes the threshold of the continuum, which is now the ground state of energy of double well potential, which is below than the ground state of the single well potential. So that's why we have an additional component of the continuum here. So the question, if we have any bound states below the continuum, and the answer is depends how strong is the potential which defines the waveguide. If the coupling constant is small enough, so the ditch is say shallow, then there is no spectrum. However, if the coupling constant is large enough, so then this turn can produce a discrete spectrum, and here is the picture which shows that this bound state is just localized in the turn. This result was also generalized, and so so it was generalized. I think I have to run because I'm looking at the time, so I will skip some details. And I would like to go to the waveguide, which is locally deformed. So I assume again that we have asymptotically we have straight strips, and I assume that we have a general local deformation, which can be based that we just form in such a way that we add something or we remove something, and then we can write the Hamiltonian, and the Hamiltonian is kinetic part and the potential part which models the waveguide. And we can discuss the questions like continuum, which is actually already answered this question, then the question about the discrete spectrum below continuum, then one can show that there are bound states in continuum. This is a very interesting phenomena, and these bound states can go to the resonances. So this, actually, I opened my cards here. Now I would like to justify these statements in my in the rest of my talk. But in between, I would like to ask you how much time is I still have.
I believe 10 minutes.
Okay. So the continuum is just actually, this question we already discussed. It starts from the ground state in the transversal profile, and the continuum is preserved. We locally deform our waveguides. It's preserved because the continuum is a very stable, is stable under such a local deformation, and we can ask the question about the existence of discrete spectrum. Of course, this question is very general, and it cannot be answered in such general formulation. However, we can just take, for example, asymptotics, and let's take the such a waveguide which has a roof with deformation, and this deformation is just defined by function f multiplied by epsilon, and if we go with epsilon to 0, then it's getting straight, this waveguide. And now we can ask the question: does it produce bound state in this system? And the answer depends on the integral of this area. So the integral is just the integral of function f. So it depends on the area of this what is related to the hill, and this what is related to, say, valley. And if the integral is bigger than 0, then one can show that there exists exactly one discrete eigenvalue below the threshold, and it has such a asymptotic form. So let me comment. It maybe looks complicated, but there are some intuitive things behind. So the first number is just the threshold of the continuum, and here is the first asymptotic term, and here is a contribution of the integral of which defines the deformation. Here are some physical parameters. So on the other hand, if the integral is less than 0, so this part is less than this part, then there is no bound state, and in the limiting case, one can show that for generally the question is open, but one can give example that there exists exactly one eigenvalue below the threshold for sufficiently small epsilon. Here is some numerics, which is for the waveguide, which has a contour here, a green contour, and we see here there is a bump, and this bump produces bound states, and we see that these bound states are mainly localized in the bump. Okay, so I promised you. Okay, I'm sorry. I promised you also a couple of words about bound states in continuum, and there should be a special reason for the bound states of continuum. And let's look to the waveguide with a mirror symmetry, and I chose that. Let's take such an example, and which is also asymptotically straight, and let's see what happens here. In such a case, here is a little bit surgery of this waveguide, and I would like to. Okay, let me back here. So we have a mirror symmetry. So let us use this mirror symmetry. The symmetry is with respect to x1. So let us cut this waveguide, and let's take only a half plane, and let's put an impenetrable wall here. So we have a half of waveguide and half living in a half plane with Dirichlet boundary conditions here. And in such a case, we can just here is this half of our waveguide. And if we look here, what happens with energies of particles is that we have a half of strip here, straight strip, and that's why the continuum of such a system with Dirichlet boundary condition is pushed up. So here is the number. So here is the number EVD, which is about EV. because because of two reasons. We have half of waveguide here. This is one reason, and the other reason is that we have unpenetrable wall here, which has also tendency of pushing up the spectrum. And we can have also the discrete spectrum below, which is due to this purple component deformation. And now, if we just back to our original symmetric waveguide, these bound states, they survive this procedure as an antisymmetric eigenfunctions. But on the other hand, this is just described here, but on the other hand, we have a continuum which starts from the original number V. So these numbers, say violet dots, they are nothing else but embedded eigenvalues. But now, here is again numerics with the symmetric waveguides, which is so we see that the eigenfunctions are localized in the in some of them as antisymmetric. And they are localized in the deformation area. So if we deform now slightly our waveguide, the original bound states, they are not anymore bound states. They probably go to the metastable states. And I would like to deform my waveguide a little bit. And I would like I don't want to involve you into details, but a little bit means that the area of deformation is small. So if epsilon is small, then the area goes to 0, and we get again to the symmetric case. And if we want to see whether we have metastable states, we can look to the resolvent and to see what happens with the original pool of resolvent. And if the resolvent has a pool which has a complex part, then we have a resonance, and the lifetime of such a resonance is defined as the inverse of the imaginary part of the pool. Okay, so there are some mathematics behind. I would like to give you the result. So what happens with the bound state continuum after deformation? So here is answer. The resolvent has a pool, and I would like to comment now. So the first number here, which is here, is the embedded eigenvalue. So this is what happens if we do not have deformation. And here these are components which are the manifestation of deformation, are consequences of deformation. So we have the real part, and if you look at the real part, it's just the first asymptotic term. So and then what is important from the physical point of view, that we have imaginary part, and it behaves like the area of deformation. So deformation, area square actually of deformation. So deformation is responsible for the metastable states, and the lifetime will have this kind of asymptotics. I think I will stop at this point. Let me mention only that it can be generalized also to three-dimensional case, and also there are the other types of resonances in this kind of systems, which are due to the tunneling. But unfortunately, I do not have time. So I would like to thank you for your attention at this point.
Thank you very much. Let's thank our speaker. And now we have time for questions. Okay. So Professor Tkachuk, please. But just maybe here, because strange sounds appears.
So Sylwia, I'm very glad to see you here. Best wishes to all colleagues in Zielona Góra. And now my question. The question is concerning separability of motion along waveguide and motion which is perpendicular to waveguide. I understand when you have a straight line and waveguide is straight as a line, okay? So in this case, you can separate perpendicular motion and motion along waveguide. But when you have banded waveguide, it is simple problem to separate this motion, or maybe it is not separated. Perpendicular motion and motion along waveguide, yeah. This question about separability is two possible two motion.
Okay, it's not easy. So so you ask about this question, for example, here, yes, we have this, we produce these curvilinear coordinates, and one which is related to the curve, the normal one, and you have to write your Hamiltonian. So it means that you have to write your Laplacian in this curvilinear coordinates, and you obtain a big expression, and of course they are not separable. But what is important here and what is interesting here, that the first term which appears is the term which is related. So you have okay, so in the first term you have the second derivative with respect to one coordinate, the second derivative with respect to the other curvilinear coordinate. So this is Laplacian, but there are a lot of terms. And then the first term, the first dominated term, is defined by the curvature. So this curvature, one can show that it acts as an attractive potential here.
So for slowly banded is always okay in this case, yeah.
But it's not. I mean, your original question is that about separability, yes?
Yeah,
so it is not separable.
Okay. So thank you.
Not separable.
Okay.
But so Volodya, I think we can just discuss this problem.
Okay, thank you.
Okay, thank you very much. And we have one more question from Malik Mouyai. Yeah, please, this is a Zoom question.
Okay, thank you very much, Professor, for the presentation. I'm Malik from EMS Cameroon. My question is relating to the waveguides. So since you were presenting about the geometry, I'm asking myself if we can see the discrete waveguide as as another geometry of the waveguide, and if it is yes, what could be the influence of the fact that the waveguide is discrete on the spectrum of the wave?
So I'm not sure I understand the question. So you mean the finite waveguide, or
the discrete finite waveguide?
Okay.
If you have the waveguide which is discrete.
Yeah. So so here I studied waveguides which are infinite in one direction. So the spectrum is a combination of the quantization in one direction and free motion in the other direction. So if I understand correctly, your question concerns the situation where it is finite, yes, and the influence of on the spectrum, yeah.
The question is if it is finite, yes, but also discrete. So if you have the waveguide which is discrete,
okay,
yeah.
What do you mean?
Yeah, if you have a guide.
You mean the situation where it's composed on separated segments, or what does it mean in this context?
Yes, separated segments. Yes.
Yeah. So so I think it's very general question. So it may have a lot of things. So it depends how these segments interact. What is the geometry with these segments? So I think it should be somehow specified, this question, but I think it's too general, I think, though. So it can, yeah. Okay, so the case of finite segments. So what you have, such a finite waveguide will have the spectrum from 0 to infinity because it's finite. Here it's not the case because I was talking about infinite. But in the finite case, continuum is just the same, like in completely free situation, it goes from 0 to infinity. Now, if you have a finite waveguide, it depends how you define and what are properties of these waveguides and what is just the geometry between these segments.
Okay, thank you very much. And we have one more, maybe very last question from Professor Pavel Horodetsky.
Oh, thank you very much. Thank you a lot for your beautiful talk. I'm not a specialist, but I wanted to ask one question. Does it make sense to consider waveguide in the context of your research as an open quantum system? For instance, there is temperature, there's one thing, but another is you may have vibrations. And we know that in solid state physics, vibrations correspond to phonons. So is there any possibility to simulate some vibrations as an external degree of freedom and consider open quantum system with respect to them? Like same quantum semigroup. Thank you.
Actually, I think so you ask probably about optic waveguides. Yes, optical waveguides.
Yeah. Mm-hmm.
Yeah. So yeah, I don't know. Here is what I discussed here is typical quantum waveguides with it's not optical.
But still, you may consider some perturbation, you know, that you may consider as an external environment. So my question
Yes.
is, does this environment make sense, like in quantum semi?
I'm not sure. Because there is a sound. There are problems with sounds. But
Okay.
you ask whether environment. Yeah, you ask about whether environment. Yes, about influence, how the environment affects the waveguide.
Exactly, because there is a huge of quantum semi. So instead of Schrödinger equation, you consider a Lindblad equation or equation with memory effects and so on. Is there anything? Yeah.
Actually, I don't know, but I think that the question is thank you for this question. So let's put in that.
Thank you.